All right, this is going to be the lesson 4.2 on quadratics, classes math 2. And we're going to go ahead and start with the warm-up problems. And so the warm-up is just this part here. The lesson starts here. I probably should have like a line there just so you know that this will be part of the lesson. So where do two functions meet? So the question here is, I have two equations, two functions. We have f and g. And then the question is, can we find where the two meet? And what we can do is we can graph them, right? So here we have 2x plus 1. Since this is a line, you could do your start value. And here you can do your rate of change. And on this one, I would recommend making a table and plugging in the values there. So go ahead and pause the video, graph both of those, and then unpause. Oh, just a reminder, this is x squared. This is a quadratic like we saw in 4.1, so this should have a U shape to it. And then unpause when you're done. Okay, so hopefully we have this finished. I'm going to go ahead and graph this. So we have a 1 here. That's our start value, and then our slope is 2. That means 2 up, 1 over. 2 up, 1 over, and then we'll go ahead and continue in this direction. And this will give us the full graph here of that line. So we'll just connect those dots. And there we go. Now, for this one, I would probably make a table. Oh, nope, I don't know why I put 0 there. Put our x and y values. And for this one, I would recommend using maybe some negatives. Let's go -3, -2, -1, 0, 1, 2, and 3. Those should work pretty well. So if I do -3 squared, I get 9. 9 minus 2 is 7. And feel free to use a calculator on these to do that. I mean, if you can do it, if you can do it in your head, that's fine. If you want to use a calculator, that's fine. But I think the goal here is we don't want to spend too much time on these type of problems. That's why we use calculators, because if we always did this by hand, it would take a lot longer. So here's my -3 squared minus 2. So we can see that is indeed 7. And for the next one, this would be -2 squared, which is 4. 4 minus 2 is 2. -1 squared is 1. 1 minus 2 is -1. If that's 0, I get a -2. If that's 1, I get -1, 2 is 2, and 3 is 7. So those are what the points look like. I know I kind of went through it fast, but like I said, this is something you use your calculator, or you can do them by hand if you want, but I don't recommend it, to get those values. And now we'll start plotting our points. -2, 0, -2 is this point here. Then we'll notice at -1 and 1, I have -1 as the y values. So at -1, I have a point here. Oh, there's an intersection. And at 1, I have a -1 as well. So these 2 points. The next two I'm going to look at is 2, 2 and -2, 2. So 2, 2 is right here, and -2, 2 is right there. And then -3 is 7, and +3 is 7. So if I go 3 over, I go 7 up. Oh, there's another intersection. And here 1, 2, 3, and I go 7 up. And then we'll just kind of draw these out. Remember, you want to use kind of a curved line for this, because this is it's not appropriate to like connect the dots with straight lines in this case, because it is a curved function. Bring this here. So here we have 2 intersections. The first intersection is at -1, -1. And then our other intersection is at 3, 7. So -1, -1, and 3, 7. Where do they meet? At those 2 points. Now, could we find this answer algebraically? So if we remember the equal values method that we used on the project and in lesson 3.5, we could try something similar. I'll put x squared minus 2 equals 2x plus 1. And so we have this, we set them both equal to each other with the idea that when the y values are the same, that's when, let me rephrase that. These represent your y values. So when I set them equal to each other, what we're saying is we want to find what x value makes the y values the same for each function. So we want the x values and y values to be identical for both functions, and those were the 2 points. So we would do the same process that we would normally do. I have x squared. I'm going to take 2x and I'm going to flip it. It becomes negative 2x. And then if I flip this negative 2 over, it becomes a positive 2. And then this is where we run into an issue. I have an x squared and then a negative 2x. We have not run into this situation before, where we're trying to solve when you have an x squared and a minus 2x. And so there is a process for this, but we have not learned it yet. We could do a guess and check method, and we could guess different values, and if you guessed negative 1, right, that x value, this would work. You would get a true value. If you did 3, it would also work. So you could do some sort of guess and check. For example, if I did a 3 here, 3 squared is 9. I'll just do it over here. So if I did 3 squared, minus 2 times 3 says equals 3, right? 3 squared is 9. 2 times 3 is 6, so it's minus 6. 9 minus 6 is 3. So we can see 3 does work. If you plug negative 1, you should get a similar result where the left side equals the right side. So the question is, how do we solve that? And we're going to talk a little bit about that in this lesson. All right, so let's go ahead and go to our objectives. Here we're going to be talking about what we call the axis of symmetry and the vertex. Those are going to be 2 important parts. We're going to find what we call x-intercepts by graphing, and then we're going to rewrite the quadratic from factored form to standard form. So it has a lot of kind of new terms in here. Now, I put all the equations that we typically use for quadratics right here. Don't let that freak you out. We'll take them one at a time, and right now I'm kind of giving you an overview of quadratics. We're not going to have a lot of time to get really deep into them, but I want you at least to be able to see this. So I don't know how much of this that I'll assess. Just a reminder, whenever you have a test, the problems that are on the test will be on the review. So we're going to cover a number of things here, but we won't be able to test on all of this because we're just not going to have enough time to practice and get really good at it. Some of it might be on here, and you'll see that on the review. All right. This is called the standard form, and this is how we saw it in 4.1 when we saw our quadratic. You put your x squared term first, and then your x term, and then your constant next. These are 2 other forms of an equation for quadratics. We'll talk about those. The axis of symmetry, this is where the middle of the graph is. So if you see this graph has this U shape to it, that U shape, there should be a line that cuts it in half. That's your axis of symmetry, and this equation helps you to find that. And then this last one is called the quadratic formula. That's a big, scary formula, huh? We're going to use order of operations when we apply this, so it won't be so bad. We have a method that you've already learned on how to simplify this, but it looks really scary right now. Once I explain it, it won't be so bad. All right, so let's take a look at this equation here. I want to talk about a couple of the parts. So we have the vertex, the x-intercepts. I also want to include axis of symmetry, but let's talk about vertex first. So vertex, it's the highest or lowest point of a parabola. I should have left a little bit more room. I'm going to have to space this down in my next version of notes. The highest or lowest point of a parabola. And it depends if it opens up or if it opens down. This one opens upward, right? So this has a lowest point. You can have parabolas that open downwards. So I'm going to just draw a little parabola here, put a dot. So that would be the vertex there. And if the parabola opens downward, then you'd have a point here. And so the vertex is just this highest or lowest point on this. I'm going to cross this out a little bit, and we'll put x-intercepts right here. Now, we've already dealt with y-intercepts. The y-intercept was where the line hits the y-axis when we were dealing with equations of a line. And x-intercepts is where does your graph hit the x-axis. Here is where the graph hits the x-axis. These are your x-intercepts. So where, and I want to be careful because sometimes when I've used the term the graph, I'll have students think that I mean the grid. But when I say the graph, I'm really referring to this. So I guess maybe a better way to say it is where the graph of the function, or where the function hits the x-axis. So I'll put that where the function intersects, right, the x-axis. And so here, these would be the x-intercepts. All right, so we have our vertex here, and we have our x-intercepts here. So we'll go ahead and draw a line here. We'll say vertex. And then its coordinates are 1, 2, 3 to the left, 1, 2, 3, 4 down. So this vertex is going to be -3, -4. That's its coordinates. And the x-intercepts here, we'll say x-intercepts are here and here. This one is going to be -1, 0, and this one is -5, 0. And x-intercepts will always have a y value of 0 because they're on the x-axis. We're not above, we're not below, right? If you go this way, y goes positive. If you go this way, it's negative. But right here, your y value is 0. Yeah, so the other thing we were going to talk about was the axis of symmetry. Now I'm going to go ahead and draw a vertical line right here. And I'm going to dash it. Because the axis of symmetry isn't like part of the graph. You aren't getting points here. Your points are all along this curve. But this is kind of a line that we use to cut this in half. So the left half and the right half are mirror images of each other. And so this would be your axis of symmetry. And so symmetry, when we talk about something being symmetrical, it means the left half is a reflection of the right half, that they're mirror images of each other. So let's put axis of symmetry. And it is a vertical line that cuts a parabola in half. And I've been using the term parabola here. A quadratic is a parabola. Those words can be used interchangeably. I am still talking about a quadratic. This is a quadratic function, but the graph is sometimes referred to as a parabola. If you think about like radar dishes, and if you have like dish TV, they have a little dish. Those are parabolic in shape. They have this kind of curved. Now those tend to be much wider, like a much wider parabola. But this parabolic shape is something that we use quite a bit in communications equipment. So this allows, when signals hit, it allows it to kind of hit and then bounce towards the center. And so the parabolas have a lot of applications. All right, so that covers the notes for page 1. Please continue on to page 2.